Hello, all of you very wonderful people. How are you all? Today I was thinking of making, like, usually I do all these philosophical videos. Today I'm going to see if I can teach you guys a little bit about electronics. And I'm aiming specifically at people who don't understand anything about electronics. And yeah, so I'm going to be simplifying stuff. I'm not going to go into any maths or any numbers or anything like that, because I don't think it's necessary in order to grasp the fundamentals of this particular topic that I'm going to go into, which is Ohm's law, and what is all the different qualities of Ohm's law. And yeah, I'm just going to keep it really simple for you guys. So, and yeah, if you get it, if you understand this, if I've communicated it well, please let me know, because this is like a test for future videos that I'm going to release on a more professional level. So, first of all, we're going to talk about current. So you might have heard of electrical current before. What electrical current is literally, if you have a wire and you have electricity flowing through it, that what is happening is electrons are going in one end of the wire and getting pushed out the other end. That flow is called current. It's called an electric current. It's sort of like it's kind of like a water current. Like, you know, if you have a river, it's flowing, you've got all these water molecules flowing through. Well, instead of water molecules, it's electrons. And the way the electrons actually flow is, we'll start off with the metal. The metal has all these little atoms, say copper atoms, because a lot of wires are made out of copper. So you've got all these little copper atoms, and they're all sort of touching each other, and they're in a very specific shape. So they'll be like, because of their size and the way the electrons are spinning around it, they arrange themselves into a shape. So they'll either be like one after another, and then the next one's on top, or maybe one after another, and then the next one is on top, but in between the two, or whatever it might be, right? So some sort of shape. Now, a copper atom has the nucleus, and it has all the electrons buzzing around the outside. And they're all in this pattern. What happens is that you push an electron into one end of the wire, and that gets pushed into the shell that all of the electrons are spinning in, right? But that copper is like, again, this is a simplification, but that copper atom already has enough electrons. It doesn't need any more. And if you try to shove one more in, it sort of builds up a bit of pressure, and it actually forces an electron out the other side so that it can be balanced again, because it can't hold that. It's already got enough electrons in that shell of the electron, in the shell of the atom. So an electron comes in, it goes into that shell, an electron pops out the other side, and it has to go somewhere, so it goes into another atom, which then pushes the electron of that atom out of that one of them. And so forth and so on. It goes like a domino effect, pushing electrons in one side and they pop out the other side of the atom. And it goes all the way along until the end of the wire. And that's the physics of how electrons flow through a wire. They actually just sort of push their way through all these atoms and then out to the other side. Just going through shell from atom to atom from electron shell to electron shell, and they get pushed out the other side. Now, current, electrical current is whenever we measure current, we measure it in amps. And what the measurement of amps actually is how many of those electrons are passing through the wire at one time. They've got they go in one hour, so many electrons flow through, right? And by measuring that, we can measure the current. But that's what we're measuring, electrons per second, basically, in a simplified way. It's actually like a certain number of electrons per second, but semantics, it doesn't matter. The point is that it's how many electrons are flowing through in a second. And that's what, and we'll call that 1 amp, 2 amps, 3 amps, whatever, depending on how many electrons are flowing through a second. And we have machines that can measure that quite easily. The next one is voltage. Now, with voltage, the voltage is just how hard that electron is getting shoved in one end of the wire. If it's getting pushed really hard, and they're just like pumping in electrons really hard into there, then that's a high voltage. If it's not pushing very hard, we call that a low voltage. So the more of this sort of pressure on the back of these electrons there are, the more voltage, the higher the voltage we actually get out of that. And so I hope you can see now, or you can imagine what's happening in this wire. Electrons are getting pushed in one end. You imagine them like little balls getting pushed in one side and getting pushed into an atom. And then as that one pops in, another electron pops out of that same atom, which then continues the process. And I think if you think about it, the voltage and the current are closely linked, right? If you have a high voltage, then you're going to have a higher current, because more pressure is going to push more electrons through those wires, right? So, voltage and current are linked. More voltage, more current. Okay? Next thing though, the next one is resistance. Now, remember how I said the atoms are arranged, the metal atoms are arranged in a very particular pattern, in a particular shape that they just happen to be comfortable sitting in, right? Well, what would you like me to do? I'll just slow down. That's okay. These electrons, these atoms are arranged in their shape, and the electrons are coming into one atom and getting pushed out of the other into the next one, and so on and so forth. Now, every time the electron gets pushed into an atom, it kind of bumps into that atom. It kind of bumps into that atom. And then eventually the other atom, the electron pops out the other side of the atom. When it bumps in, it actually gets slowed down because it has to sort of change its direction. It's like going through, hits the atom at one angle and sort of like, oh, now I have to change. So it slows the electrons down. It's literally resisting the flow of the electrical current. That's what resistance is. It's slowing down the electrons from flowing through whatever material that it is. And depending on the shape that these atoms are, among other things, but mainly this structure, this geometric structure that all these little balls of atoms are arranged in, whatever shape that is going to going to create more resistance or less resistance. Something with, when we're talking about normal materials, such as copper, aluminium, steel, carbon, all these sort of things that are used for this purpose, for conducting electricity. Some of them provide a very smooth path for the electrons to flow through, and other materials will produce this, like they have to like duck and weave and try and get through to the other side, and they keep bumping into all these atoms on their way and they slow down. Do you imagine this? Imagine these electrons flowing in all these zigzag patterns. They have to go this way, then they have to stop, and then go this way. It's not quite like that, but it's similar. It's similar to that. And so you can imagine there's two things here. One is the shape. What shape is what path does the electrons have to bounce around inside these atoms, right? The other one is how long is it? So there's a material called carbon that's used in resistors. Resistors are devices specifically designed to slow down the current flow of electrons. And carbon has the shape of the carbon that they use, of the pattern of these atoms, is one that causes a lot of this sort of action. Now, if it only has to flow, if the current only has to flow through a small amount of carbon, then it doesn't have to do this so much. But if it has to go through heaps, then it slows down a lot by the time it gets to the other side, because it has to go through this massive distance to through there. So they can control this very accurately, and I think they can. They can control the resistance of that resistor very accurately just by the size of it, assuming the purity is high and all this sort of stuff. Now, one last thing is that if you push a lot of current through a resistor, right? You push a lot of electrons per second through a resistor. You're pushing them with high voltage, pushing them through a resistor, so you have a high current flow of electrons, right? Because the resistor has a shape, an atomic shape, like the way they're arranged, to do this thing, and the atoms, the electrons are bumping into all these atoms, right? They're bump, 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 bump. When it hits the atom, that atom will jiggle a little bit. It'll vibrate a little bit. And that is a type of energy. That vibration is a type of energy. That type of energy is specifically heat, as heat energy. So if you push 1 amp through a resistor, or then you push 1 amp through like a copper wire, the resistor is going to heat up more, because there's more collisions that are causing more vibrations on the atomic level. So it's not something you'll be able to feel. You won't be able to feel these vibrations, but you will feel it in the form of heat, because anything that is warm is just atoms and stuff jiggling and vibrating. That's heat. So you can now see that voltage and current are intertwined. But you can also control the current. So you can control the current by two ways. You can change the voltage, or you can change the resistance of the wire, or whatever. you know. If you increase the resistance, if you put a resistor in there that has lots of resistance, then the current flow is going to be decreased, because each time it collides with an atom, every time an electron collides with an atom, it slows down a little bit, and it slows down a bit less, a bit less, a bit less, a bit less. The speed goes less and less and less, right? And by the time the electrons have flowed out the other side, they're going a lot slower than they were before. So we can control the current using voltage or with resistance. And voltage, we could just use different batteries that have higher voltage, or there are so many different ways to change the voltage that I won't go into it. And we can also see that we could actually work out what the voltage is if we know what the current is and the total resistance of that that circuit, right? If we know the current, we've measured the current, and we've measured the resistance, then we can work out the voltage, sorry. We can work out the voltage through the current and the resistance. In fact, we can work out any of those if we have two of the other ones. We can work out the current with the voltage and the resistance. We can work out the resistance with the voltage and the current. And of course, all that other, that third one, I've already forgotten. So, that's basically, and this interaction between these two, there is a formula. You can look it up online if you're really desperate, but the formula to work out these is called Ohm's law. Ohm's law is that, it's a formula. How to work out the voltage, how to work out the current, or how to work out the resistance using the other two parts that you actually have, right? And that's Ohm's law. That's why Ohm's law works. More importantly, that's the point of this video. What is Ohm's law? What actually is it? Not the formula, but why does it work? So now I hope that when you think of electricity, now that you know these three fundamental things, voltage, current, and resistance, you can visualize a bit more easily what is happening inside a light bulb or a speaker or whatever, your heater, your electric heater. Why is that electric heater getting so hot? Oh, there must be a lot of current, and that wire that's getting glowing hot must be high resistance as well. So, is that all I was going to say? Yes. Yes. That's it. Let me know what you think, and enjoy your day. Goodbye.